But this model allows to calculate now what are these stresses. Yes, sir.
In some of our other classes, we have like approximations for sigma H max, which is the overburden stress plus the minimum stress divided by 2, is like what we've been told.
Okay.
And also.
Well, that's just an average, right?
Yeah, it's just an average.
Which is better than nothing, but
and then
it's not correct in most cases.
And then what about sigma H min being approximately equal to Zobac's equation?
Well, you mean this equation?
Oh, no, just for sigma H min being approximately equal to Zobac's.
So what do you call Zobac's equation?
It's that fracture equation, like 0.32 times the stress of the overburden minus pore pressure, and that all in parentheses then plus pore pressure.
Well, let's say that this is 0.25 and this is 0.25. What is the value of that?
0.33.
0.33, right? So we're going to see two methods to calculate horizontal stress. One is based on linear elasticity, and it is this one, and you see that it gives a similar value to what you were mentioning as the Zobac's equation. Actually, this one that uses the Poisson ratio is called, probably we should come back over here. This one is called Eaton's equation. And something alternative that we're going to use later on to estimate horizontal stress, it's another type of equation that was proposed by Zobac, but not based on elasticity, but based on failure. And we're going to see that that coefficient is similar, but also depends on the location, depends on the tectonic stress. So this 0.33 is just valid for conditions in which there is normal faulting stress regime and there are no tectonic strains. If you don't have those, then you need to go through this larger development. So you're going to have to calculate these stresses a lot in homework, in exams, and because of that, I like to propose here a procedure, okay, a general procedure to calculate horizontal stresses with elasticity. So, as I was telling you, this is just one of the methods. Later on, we're going to see another one, but we need to go through a few more things in order to understand that one. Okay, so this method is going to consist of, in general, 5 steps. Let's say that you go to a particular location where you want to compute what is the horizontal stress. And I'm going to make it general. It's going to be a place offshore. Wait. That should be seafloor. The first thing that you do, always, first step is compute SV. You know how to do that, okay? It's all the weight of the rocks and water on top of the particular location in which you want to compute stress. So this one is going to be SV, and our objective here is to compute the horizontal stress. Step number 2, you have to determine what is pore pressure. Here there are 2 options. One option is that it's hydrostatic, and in that case, pretty easy to compute that. And if it's non-hydrostatic, I might sometimes give you directly what is the value of lambda p. Well, remember lambda p is pp divided by sv. So you know lambda p, you know sv, you know pp. Or some other cases, I could give you what is the porosity of the shale, and you have to figure out that from the equations that we have already seen. So remember, if the porosity of the shale is more than it would be expected at that location, then the pore pressure should be higher than hydrostatic. So now you have SV, you have PP. Third step, you compute effective vertical stress, which is just the difference between SV and PP. And once you have that, and only after you have that, you can apply the equations of elasticity. And for example, if you had your tectonic strains to be zero in both directions, then you know that sigma h is just going to be simply given by Eaton's equation, and just going to be that. You have sigma b. If you know what Poisson ratio is, you know sigma h. And if tectonic strains are not zero, then you have to use this long equation that I wrote 5 minutes ago. But you also have it, okay? In this case, also you need the Young modulus. If you don't have the Young modulus, then you cannot compute that. But here we're not done yet, okay? The last step, because we want to compute total horizontal stress, is going to be to add pore pressure to the effective stresses. So the minimum horizontal stress is going to be equal to sigma h mean plus the pore pressure, something that you already know, and the maximum total horizontal stress is going to be sigma h max plus pore pressure. Notice that you always apply the elasticity equations to effective stresses, not to total stresses. First, convert everything to effective stresses, and then you can calculate the total stresses. Eventually, you're going to see that depending on the application, sometimes we need to calculate effective stresses, some other times we need to calculate total stresses. Effective stresses are more useful when we talk about rock compaction, rock failure, wellbore stability. Total stresses are more useful when we talk about hydraulic fracturing. So, if you follow this procedure, you're going to be able now to calculate horizontal stress using elasticity and knowing the properties of the rock. Later on, when we move to the second method, you will see that the only thing that we have to replace is that instead of elasticity, we'll assume failure or plasticity. But it's going to be exactly the same procedure. Okay, let me see what's next. Do you have any questions? Yes.
So I have a question about your nomenclature.
Yes.
So like you say SV, and then you have SH min, SH max, and
Yes.
you call it SH min, SH max total stresses, right?
Yes.
And so is SV total vertical stress? Does that also apply to SV?
Correct.
Okay.
This is total vertical stress. S are always going to be total, and sigmas are going to be effective. So these are total, these are effective. And since you bring that, topic into, since you mentioned that, it depends. Some people use different nomenclature for effective stress and total stress. I follow this one, which is assuming the book from Zoba. So just to be talking in the same with the same symbols, I'm using the same S total, sigma effective. Okay, let's see what time is it. I do have time. This is what you need in order to solve problem number 5. Let me check. I think it's a simpler version in the notes. So we're going to talk about this one on Friday, okay? But I'm pretty sure you can already do this one because we did number 4 in class. We didn't do it with numbers, but we did it theoretically. And now we're going to talk about compressibility, but the last problem, number 5, is about computing stresses with a given tectonic strain, as you can see here in the bottom. So you just have to follow that procedure. It's very important to me that you get this procedure right, because whenever we talk about later on about wellbore stability, about hydraulic fracturing, about fault stability, everything starts by knowing what is the initial state of stress. That's the first thing that you do. And same in exams, if you have to do this first and you get it wrong, probably you get the rest of the problem wrong, okay? So knowing how to do this, it's going to be very important, and I'll try to make sure that you learn that by the first exam. Okay, so I think I'm done with this. Let's now talk about compressibility. This is just one example of how to use linear elasticity to our problems in petroleum engineering. Now we're going to see another problem, another application, which is related to reservoir engineering. In reservoir engineering, most of the time, what you want to do is you want to solve what is called the diffusivity equation, where that tells you the variations of pressure as a function of time in a given reservoir with a given permeability, fluid viscosity, and that depends on the total compressibility. And those pressures also depend on space. So this equation for one dimension, diffusivity equation in one dimension, something you have already seen in reservoir engineering and petrophysics. Well, I'm not going to get into this equation. I want to discuss what is this compressibility. You know about permeability, you know about viscosity. Let's talk about compressibility. This is total compressibility, and the total compressibility is a function of the compressibility of the constituents in the pore volume, like the gas, the compressibility of water, and the S are saturations, and compressibility of oil, plus another term, which is the rock compressibility. The rock compressibility tells me how much the rock is going to change pore volume due to a change in pore pressure. And let's make a schematic in order to understand what's going on here. Let's say we have a perfect anticline, capped by a shade. We have a reservoir over here. We put a wellbore. You do perforations, and you start producing. Let me plot here as function of time the vertical stress and the pore pressure. You know how to calculate vertical stress, okay? Vertical stress, we said, is all the weight on top of this. I'm particularly interested in this case on an element of rock somewhere around here in the reservoir. That's squared. That squared is going to be subjected to a vertical stress SV. In order to produce, I need to lower the pressure, right? So pressure with time, let me make it simple. I'm going to assume that pore pressure is going to decrease with time. And we know that vertical stress has to be higher than pore pressure because otherwise we will have a hydraulic fracture there. And let's say that starts somewhere over here, over there. My question is, what happens with SV with time? Does it change? Does it go up? Does it stay flat, or does it increase?
It depends how much sediment is deposited on top of it.
Well, let's say that there is a lot of sediment here.
The sediment.
It changes
does it
with
get-
time
yeah.
because there's little particles of sand being added to it. It's like negligible, I guess.
I'm not quite sure about that. But let's continue with your train of thought. You were saying?
Right. That was what I was saying. Like, what if there's stuff getting added on top of it? Then
Well, I mean, what is going to get added here? Probably we'll have a few tracks over here, right? And probably a few pumps and full of sand, but that's negligible. That's very small.
So if SV is like function of bulk density,
Yeah.
then if you